Hello everyone, welcome to the third lecture of Signals and Systems. In this video, we will review the system and then see its classification, and then we'll see an example of a system, and finally we'll see the properties of a system. So let's get started. So we already saw a system is nothing but an interconnection of components, devices or subsystems, and it is used to transform the incoming signal or to extract some additional information, right? So, system is an interconnection of devices, components, or subsystems, and it transforms the incoming signal or the input signal or extracts additional information from it. So for our discussion, we broadly classify the system into two types. So classification. System. So the first one is continuous time systems. So as the name indicates, it takes a continuous time signal as an input and delivers a continuous time signal as an output. So it takes in a continuous time input signal and delivers a continuous time output signal. So this can be represented using a block diagram like this. So this is the system, let's say continuous time system, and it takes in a continuous time signal and gives out a continuous time output signal. So it does some processing inside. So the second class of signals is called as discrete time systems. So again, this takes in a discrete time input signal and gives out a discrete time output signal. So it takes in a discrete time input signal and gives out a discrete time output signal. So how do we write this in the block diagram? So we have the discrete time system and a discrete time input signal. So it is represented by x of n. We already discussed it. And the output is again a discrete time signal. So again, as we already discussed, this output signal is nothing but a function of an input signal, right? So if there are more than one input signal, and there can be more than one output signal also. So there can be x1 of t, x2 of t, and so on, xn of t. And the output can have y1 of t, y2 of t, and so on, ym of t. So this is an example of multi-input, multi-output. And since the signals are itself continuous time, it is continuous time continuous time system, right? And each of these yi of t is nothing but some function of xi of t's, right? x1 of t, x2 of t, and xn of t. Okay. So now let us see an example of a system. Example of a system. Okay, so I will draw a box. So let's say this is the input, some Vi of t. Okay, and it goes to a resistor and then a capacitor. So this is a simple RC circuit, right? R and C. And this is the output, VO of t. Okay, and now this is a continuous time system, and let's say we want to find the relation between V out of t and V in of t, right? So we can apply simple laws, right? Let's say the current is I of t. So the same current I of t will be flowing the capacitor. So writing first the simple Ohm's law, what will you get? I of t is nothing but Vi of t minus VO of t by R, right? And we know the current and voltage relationship for a capacitor. So the I of t is nothing but C dVc of t by dt. But what is Vc of t here? The voltage across the cap is nothing but VO of t itself. So it is C into dV of t by dt. And we want to eliminate I of t and get the relation between V0 of t and Va of t. So we just equate the right hand sides. So Vi of t minus Vo of t by R is equal to C dV0 of t by dt. So you can take the R to the other side. We'll get Va of t minus Vo of t is equal to RC dV0 of t by dt. So let's bring all V0 of t to one side. So what will I get? RC dV0 of t by dt plus V0 of t is equal to Vi of t. So we get an differential equation relating the output voltage to the input voltage, right? So this can serve as the definition of the system itself. So that is all with this example. So next I want to discuss interconnection of systems. Interconnection of systems. So I can have more than one system, right? The signal going through more than one system. So let me call it system 1. So there is an X of t and there is an output W of t, let's say. And I can feed this W of t as input to a second system. So system 2. And then I get the final output as Y of t. So this is like the systems in series, right? So this is the first series connection of systems. And this is also called as the cascade. One after the other, right? And second, they can be in parallel, correct? So I have the same signal X of t going through two systems. System 1 and then system 2. And there can be like n number of systems, it's not a problem. And then we take these outputs, let's say W1 of t and W2 of t, and add them, right? And we get some Y of t. So this is parallel connection of systems. And we can also mix them. So I'll take X of t. Let's say I feed it through system 1. and in parallel I put it through system 2 and another system in series with system 2, so system 3, and then I take these outputs and add them. Y of t. So this is like W1 of t, W2 of t, W3 of t. Okay, this can be called a series parallel connection. But in all these cases, if you see, the information is flowing only in the forward direction, right? From x of t to W of t to Y of t. But there can also be information flow in the backward direction. So that is called as a feedback interconnection. Alright, so I have x of t. I pass it through some system 1. Okay, I get an output y of t. But I also branch this output y of t and pass it through another system called system 2. And then the output of system 2, let me call it W of t, I feed it back to the input. Okay. It can be an adder, subtractor, anything. So this kind of systems interconnection are called as feedback interconnections. Okay. So next we'll see the properties of systems. So properties of systems. So first property we are going to be looking at is called as memory. So if you have a simple resistor, let's say this is a resistor. So I of t is the input and the current flowing through this is, say, the output. Then how is the relation? Current is equal to voltage by resistance, correct? So if you see whatever is the output, it is depending on the input at that same time instance, correct? So we can say there is no memory. So to put it more formally, if the output of the system for each value of the independent variable, which is nothing but t here, right? Independent variable at a given time is dependent only on the input at that same time, correct? So as examples, you can give n number of examples. One simple example is x square of t. It can be any complicated also, plus 3x of t. But you can see only t is involved. So if I want to find y of 0, y at time t equal to 0, then it only depends on x at time t equal to 0, right? It doesn't depend on any other time instant. So then it is called as memoryless system. Memoryless system. Okay. I'll just rearrange. It is then called a memoryless system. So on the other hand, what do we have? We have a system with memory. So system with memory. Same definition, but it can depend on the input at different times, right? So output at a given time also depends also is not necessary, depends on the input signal at other times. So simple example will be y of t is equal to x of t minus 2, something, some t naught, where t naught is not equal to 0, right? And it can also be, this is like at a earlier instant, it can also be at a future instant, right? So you may ask how the system will know what the future signal is. So it always needn't be time, right? It can be like spatial coordinates. When you're doing image processing, you can have, like, you have pixels. So let's say this is the x-axis and this is the y-axis. And they are represented in form of arrays, some a of n, m, kind of like this. So in this case, if you're at this point, you actually know what is there either after it or before it. So this t is, for convenience, we are saying it as time, but it needn't be just time in all cases. So t plus 2 is absolutely possible. Okay. So as a physical example, if you take a capacitor, right, with value C, let's say I feed in a current II of t to it, and I take the output V of t. So you know the relation. So II of t is nothing but C d V0 of t by dt. But if you want to find V0 of t in terms of II of t, what will I do? I need to integrate. So V0 of t is nothing but 1 by C integral minus infinity to t, right? Because it is at the instance t. And II of t dt. So you can see, like, it is depending from minus infinity to that point t, all the values of II of t, not just at that particular instant. So it is a system with memory. Okay. So moving on, the second property we are going to see is invertibility. So what does invertibility mean? Okay, I have some x of t. I pass it through system 1. I get some output y of t. And if I pass it through an invertible system, so this is invertible of system 1, then I should get back the same system x of t, right? In other words, the cascade of this system should act as an identity system. Correct? So what does identity system mean? Y of t is nothing but x of t itself. For example, if system 1, let's say, system 1, y of t is nothing but 2x of t, right? And system 2 is y of t is equal to half x of t. So then what will be the cascade of these two systems? It will be, so let's call it this as x of t as input, w of t as the output of first system, and y of t as output of second system. Then what do you have? W of t is nothing but 2 times x of t. And what will y of t be? It will be half of w of t. But we know w of t is 2 times x of t. So it is half into 2x of t. Half cancel. Then we get y of t is equal to x of t. So this means identity, which means system 1 and 2 are inverse of each other, right? Or system 2 is an inverse of system 1. So, but what is the condition that a given system will be invertible or not, right? So if the system has unique outputs for unique inputs, then it is called as, then the system can be said to be invertible. In other words, the mapping should be 1-to-1. So the mapping should be 1-to-1. Right? For example, if you take x square of t, y of t is equal to x square of t. For some x of t, let's say for x of 0, the value x takes is -2, and x of 1, the value x takes is 2. But in both these cases, the value y is going to take is 4, right? So if we have to go back from y to x, we can't say like 4 will correspond to +2 or -2. So it can correspond to both. So this is an example of a system which is not invertible, which is not 1-to-1 and not invertible. Correct? So where this property is being useful is, for example, we are sending some information. You can take your WhatsApp itself. So you are feeding in some message, which is nothing but an input signal. And what WhatsApp does is, it encrypting, right? It encrypts and modifies the signal. Okay. So this is some W1 of t. And then it goes through the channel. Channel is just like you can call, say, internet, right? And then the output sits here, output message. So the input message and output message should be same. Then only we can interpret it. Whoever is sitting here can interpret it, right? Receiver. Let's call it receiver. So then this, whatever sits here, which is called as decrypting. Again, this is again in WhatsApp of his mobile, his or her mobile, right? So whatever is being encoded here, the signal transformed here, this should do the opposite of that, such that whatever signal is here, the same signal x of t also comes here. So it helps in encoding and decoding. And also ensures safety, right? Privacy. So these systems are being helpful here, right? Anyways, moving on. The next property is causality. So we already saw causal systems. So causal signals. So we already saw causal signals. So causal signals are one where their value x of t is equal to 0 for t less than 0, right? And they have value only for t greater than or equal to 0. Similarly for causal systems, right? Causal systems. So if the output at any time depends only on the values of the input at the present time or the past, right? Or in the past. For example, y of t is equal to x of t minus 3, right? So each value of y of t is depending on x of t at 3 seconds or 3 units back in time. If we consider the independent variable as time, we can say so. But if you take the example of x of t plus 2, so this is actually referring to the future instant, right? So this is not a causal system. Okay, this is non-causal. Non-causal system. And this is a causal system. So whatever the system is processing and whatever the output we are getting, it should depend only on the present input or the past. Okay. And these types of systems are also called as non-anticipative. So why they are called as non-anticipative? Anticipating is expecting something or guessing something what happens in the future. But since causal systems, like the outputs does not depend on the input signal which are having the future values, so these type of systems are called as non-anticipative systems. And hence these non-causal systems are also called as anticipative by the same logic. Okay. And you may ask, can there be some anticipative systems? Yes, right. I mean, the non-independent variable is not time. It is, of course, possible, as I already explained with this pixel case, right? So it is possible to have a non-causal or anticipative systems. Okay. So the next property we'll see is stability of systems. Stability. So we call a system as stable. System as stable. In other words, a stable system is nothing but when a bounded input, all bounded inputs give a bounded output. So you can call all or a. Correct? So what does bounded input mean? Bounded means its value is finite and it is not infinite. So for example, if you take any signal, right, a constant signal, x of t equal to 2. This has a value only 2 throughout, and the value 2 is finite in itself. So this is a bounded signal. And if you take the unit impulse function, this goes to infinity at t equal to 0. So this is an unbounded signal. So if we restrict our inputs only to the bounded signals, then we should get the outputs also to be bounded. In that case, we say the system to be stable, or we say it is a stable system. Let's see some examples. For example, you can take any number of examples. So x of t equal to x square of t. So as long as x of t is bounded, the square of that also is going to be finite, right? So in that case, this is a stable system. And if you take another example, y of t is equal to, so sine of x of t. So if you see the inputs, output is going to be limited between +1 and -1 always for any bounded x of t. So then we'll also see some unstable systems. So one example is y of t equal to dx of t by dt. So this, if you take u of t is a bounded signal, right? Because its maximum value itself is 1, and for t less than 0, it is going to be 0. So this is a bounded signal. So now, if you differentiate u of t, what do you get? du of t by dt is delta of t. But this is unbounded, correct? So the system itself is unstable. Okay. So for stability, actually, for every bounded signal, the output should be bounded. But to prove that it is unstable, you can just take one example of a bounded signal giving an unbounded output. So that is sufficient to show that the system is unstable. So the next property we will be seeing is time invariance. So generally speaking, what time invariance mean is that So if you're doing some experiment today, and even if you do the experiment tomorrow, it should give you the same results. So if, let's say, you're performing some experiment with some mass, you can take the pendulum, right? So mass and length. So if all these parameters are fixed, and you're just doing it in some other point in time, even after 10,000 years, if you do, the physical laws are same. So whatever results you get today, you should be getting the same results during whichever time you perform also. So this is the general concept of time invariance. So in our case, we say a system is time invariant. A system is time invariant if a time shift in the input results in an identical time shift in the output signal. For example, let's say this is the input signal and this is the output signal. So if I just move this input signal by, let's say, some t0 units, then the output signal also should move by t0. But every other thing should be same. The shape and the points, everything should just get moved by t0. But the shape and other things should remain same. So mathematically, how do I describe it? So let's say if the system is described by some function y of t is equal to f of x of t. So if I just move the signal by t minus t naught, f of x of t minus t naught, then it should be equal to y of t minus t naught. Okay. So if it is some other y prime of t which is not equal to y of t minus t naught, then it is called as time varying signal. So this is time varying signal. And this is a time invariant signal. So let's see some examples. So first let's see some examples for time invariant. Sorry, this is system, right? Sorry. System. Okay. Yeah. So time invariant system. So first example, let's take y of t is equal to sin x of t. So now if I take some other signal, x1 of t is x of t minus t naught. Okay. Then what will be y1 of t? It will be sin of x1 of t, right? But x1 of t, I can replace it with x of t minus t naught. So this is my new output. And what is the time shift of the old output by same t naught? It will just be sin of x of t minus t naught. So you can see that y1 of t is equal to y of t minus t naught. So the output is also resulting in a time shift of the same number, right? Same t naught. So this is an example of a time invariant system. So next we will see time varying system. So if you have y of t is equal to tx of t, right? So then let's again assume x1 of t is equal to x of t minus t naught. Okay. So what will y1 of t be? It will just be replacing x of t with x of t, x1 of t. And x1 of t is nothing but x of t minus t naught. Okay, now let's try to time shift the output and see the previous output. So y of t minus t naught. So for time shifting, what I have to do? I just need to replace all t with t minus t naught. So it will be t minus t naught into x of t minus t naught. So now if you see, this is y1 of t is not equal to y of t minus t naught, because this additional t naught term is coming, right? And it is expected. So this y1 of t is not equal to y of t minus t naught. Hence it is a time varying system. Okay. So next we'll see the last property, which is linearity. So when do we say a system is linear? We say a system is linear if it satisfies two properties. If it satisfies, so the first property is x1 of t plus x2 of t. So if you send in an addition of signals, input signals, then it should give you an output which is also an addition of the individual outputs. Okay. In other words, if you just send an x1 of t, the output is y1 of t. And if you just send an x2 of t, it gives y2 of t. And then you try to send an addition of x1 and x2, which is x1 of t plus x2 of t. And you need to get an output that is sum of the individual outputs you got previously, which is y1 of t plus y2 of t. So this is one property, and this is called as the additivity property. So this is not just for two signals. Even if you have n number of signals, here also you should have the sum of n number of output. But it is just sufficient to just show it for two signals. And then the second property is the homogeneity or scaling property. So what it means is, if x1 of t gives y1 of t as output, then I multiply it with some a times x1 of t. Then the output should be a times y1 of t. So whatever times I scale the input, the same scaling should happen at the output. So this type of system is called as linear systems. And together both of these properties, we can say that a x1 of t plus b x2 of t is nothing but a y1 of t plus b y2 of t. So this is the superposition property, right? So this is just nothing but the extension of additivity and homogeneity, both combined. We can write it like this. And what does superposition mean? So if you want to if you are giving input as this ax1 of t plus bx2 of t to a system, ax1 of t plus bx2 of t, and if the system is linear, then to find output y of t, what you have to do is, you can just first send in x1 of t, one of the signal, ax1 of t you can send it, or x1 of t alone you can send, and you can find y1 of t, and then x2 of t you can send in and find y2 of t, and then you can just write y of t as a y1 of t plus b y2 of t, superpositioning them, right? So this is a property of linear system. So all these are same system. Let's call it system A. This is also system A. System. Otherwise it will not work, right? Obviously. And the other thing is, this A and B can also be a complex numbers. See. So let us see some examples. So the first system, let's take y of t is equal to 2x of t plus 1. So you may think that y of t is linearly related to x of t. But let's go ahead and check if this is really a linear system. So first let us try the additivity property. So x1 of t gives y1 of t, which is nothing but 2x1 of t plus 1. Okay, x2 of t gives y2 of t, which is 2x2 of t plus 1, right? And now we send in the sum, x1 of t plus x2 of t. It will give some y of t. And what will be the output y of t? It will be 2 into x1 of t plus x2 of t plus 1. But what is y1 of t plus y2 of t? It is nothing but 2x1 of t plus 1 plus 2x2 of t plus 1, which is nothing but 2 into x1 of t plus x2 of t plus 2. So if you see here, it is plus 1 and here it is plus 2. So they are not equal to y of t. Hence, they are not linear. So to prove that it is not linear, even if it does not satisfy any one of the condition, then it is non-linear, right? So the system is non-linear. Correct? So, like, even though it is like a linear relation, when you see it as a function, you actually should not have any constants, right? Because of this constant only, we are getting this difference of 1 and 2. Suppose if we took y of t equal to just 2x of t, then this constant wouldn't have appeared. So this system is perfectly linear. It is a linear system. So another good check is, if you see in the second, a can be any complex number, right? If you put a equal to 0, which is nothing but you are passing in 0 input, then it should give 0 output, right? So that is one good check to actually prove that it is not linear. If you check here, if you do a 0 input, the output y of t is actually going to be 1. It is not 0. So from that you can still prove that it is not a linear system. But to prove that it is linear, it is not possible, right? So we'll see another example for that. So y of t is equal to x square of t. If you see here, 0 input gives 0 output. So is it linear? What do you think? Yeah, it is not linear actually. So this 0 input, 0 output only, it is done for proving that it is non-linear. If you want to prove it as linear, you have to go for the superposition. Okay. So I will take x1 of t. In this case, I will just simply use the additive property. So x1 of t gives y1 of t, which is x1 square of t, and x2 of t gives y2 of t, which is x2 square of t. And what does the sum of the inputs give? It gives some y of t, which is x1 of t plus x2 of t whole square. So this is x1 square of t plus x2 square of t plus x1 of t, x2 of t. 2 times x1 of t, x2 of t. But y1 of t plus y2 of t is nothing but x1 square of t plus x2 square of t. Only this. So this extra terms comes. So then this is not equal to y of t. Right? So this is again not linear or non-linear. Okay. So what all properties we have seen so far? We first saw about the memory system, property of a memory of a system, and then we saw the invertibility property of the system, then causality, stability, and then we saw the time invariance property, and finally we saw the linearity. So these are the basic properties of the system. So at first shot, you may think that you have got the definitions properly and everything, and you may be able to solve questions. But when you actually solve the questions, you will find many difficulties while solving. So, and also you will learn a lot while solving more questions. So what I would urge you is to take the books, and this is actually the end of the first chapter, and there are lots of book back questions which are really useful. By solving most of the questions, you will actually get a very good understanding of the system properties. So that's it for today. See you later. Bye.